In this video, we will discuss what is considered really important information for an equilibrium test in AP Chemistry. Now, whatever shows up in this video is definitely important, but if something is left out for whatever reason, that doesn't mean it's not important. Okay, so how we're going to do this is I'm going to go through some example problems and example topics, and you should pause the video and work through them and then check with the video before moving on. Okay, so equilibrium is a state where the forward and reverse reaction are at the same rate. And with equilibrium, we typically have something called an equilibrium constant, and our equilibrium constant, that is K, and K is going to be equal to the products divided by the reactants. And of course we have to exclude solids and liquids, and the reason why we exclude them is that their concentrations do not change. If my numerator is really big, that means K will end up being greater than 1, and that will be product favored. And here's what we know, that's product favored. We could call that spontaneous. We could call that thermodynamically favorable. We know delta G would be negative because it is favorable to lose energy. And then the voltage would be positive. Okay, so we kind of know all of that, but we don't know how fast the reaction would occur. That would be kinetics information, but it is definitely important to know this part right here that is boxed. 110% I would know that. Okay, so K is dependent on temperature. And so with a lot of the examples that we're going to work through, they will give us a temperature. And it's not that we need to use it necessarily, but it's given because that's the only time when that K value that is given would be true. So if I look at this equilibrium graph right here, I should be able to get a balanced reaction. From my reaction, I should be able to write an equilibrium expression. I should be able to estimate the equilibrium value from the chart. And then from my K value, I should be able to figure out if it's product favored or reactant favored. And here's what I know is I know that A must be a reactant because it is decreasing. And B and C must be products because they are both increasing over time. And I see that A goes from maybe about 0.8 all the way down to, what does A go to? About 0.35. Okay, and then B and C goes from 0.2 to about 0.425, and B goes from 0.4 to about 0.625. So what I can say is that B and C, they increase the same amount, so their coefficients must be the same, and I'm just going to call those coefficients 1. And then A decreases double the amount that B and C increase, so I know A is 2. So from my equilibrium expression, I know that K is equal to the concentration of B times C divided by A squared. And the reason I know that these can go in my K expression is that they must be aqueous or gas because their concentration changes over time. And so for K, what I'm going to do is I'm just going to copy this. I'm going to plug in what I know. B, I said, was 0.425. C, oh wait, I plugged in, okay, 0.625. C is 0.425, and A is 0.35. when I plug that into my calculator, I get 2.17 as my K value. And so this must be product favored because K is greater than 1, meaning that my numerator is larger than my denominator. And since my numerator is products, it must be product favored. Okay, now, what would shifting a reaction, by the way, one thing I forgot to mention on this graph is I know that equilibrium is established, let's just estimate it at about 800 seconds, because that's when the slope of my lines, all of them approach 0, and so that means that we must be at equilibrium because there's no net change. Okay, so what would a reaction graph look like if it's already at equilibrium? So I have N2O4 and I have NO2 and they're already at equilibrium. And one thing that's kind of cool is if I took K is equal to NO2 squared divided by N2O4. And at this current equilibrium, the part that is highlighted, I could say that this is going to be 2 squared from here divided by 8, and I get 0.5 for my K. Now, what happened here is I was at equilibrium and then something was added, and it tells me that N2O4 was added. So this guy was increased, and I know that because I can see that the value or the concentration of N2O4 suddenly increases. But when N2O4 increases, that's going to cause the reaction to shift right. And it will regain equilibrium in the process, and since it shifts right, NO2 will increase. And the thing that's kind of neat is that if I plug in now to this K expression at these new ratios, I should end up getting the same 0.5 value. So let's see if that works. So now NO2 is 2.2236 and N2O4 is 9.8882. Let me plug that into my calculator. 2.2236 squared divided by 9.8882. I did get 0.5, okay? And so now we're back at equilibrium, and this is just demonstrating what Le Chatelier's principle would look like in a graph. Now, one thing that we want to be able to do is we want to be able to just predict which way things will change without doing numbers. So most students are pretty okay at this, that if I add CO2, this will cause the reaction to shift right, but K stays the same. If I add some H2O, normally water is a liquid, but here it is in the gas phase, so it will affect equilibrium. This will cause the reaction to shift left, but K also stays the same. In C, there's no shift because a catalyst just gets us to equilibrium faster, and K is also constant with a catalyst. And if I increase the temperature, heat is over there, we're going to shift right. And you may remember from the beginning of this video, the only thing that changes the equilibrium constant is temperature. And so it's going to matter which side heat is on. Because we're shifting right, more products are formed. And because K is equal to products divided by reactants, I've shifted right, K has changed, and now my products in my numerator is higher. So this will actually cause K to increase. Okay, that is only because heat is on this side of the reaction. Heat is as a reactant. So you have to think through it like that, because heat could be on either side of the reaction, and I could either increase it or decrease it. And so that would impact how you think about this, okay? I would make sure you know how to do that. Now, what we should be able to understand is sometimes you will start a problem and you'll make a rice table, and for example with this one we will plug in 1.0 times 10 to the minus third for NH3, we'll plug in 1 times 10 to the minus 5 for N2, and then 2 times 10 to the minus third for H2, and you might ask yourself, well, which way will the reaction shift? When you are given values of everything to start out with, that means you have to solve for Q. Okay, and the reason why is that we don't know which way it'll shift. So Q is solved the same way as K is. So Q is equal to NH3 squared divided by N2 H2 cubed. And the thing that a lot of students struggle with is their calculator, and some students struggle to make sure H2 stays in the denominator, and don't forget to also cube it. So let's plug in these numbers. 1.0 times 10 to the minus third squared divided by N2, which is 1 times 10 to the minus 5, times H2, which is 2 times 10 to the minus third, and that will be cubed. And when I get Q on this one, I end up getting 1.25 times 10 to the 7th. Okay, large number. So what I'm going to do is I'm going to say, okay, here's a number line. K is where my reaction will always return to, and K for this reaction is 6 times 10 to the minus 2. Q is all the way over here. Q is much, much larger than K in this problem, in example A. And so what I know is that Q is going to shift back left to get back to K, and so the reaction shifts left. Okay. In B, we're going to solve this the same exact way. So I'm just going to copy this. I got to plug in my numbers to see where I'm at, and my ammonia is 2 times 10 to the minus 4 squared divided by 1.5 times 10 to the minus 5 times 3.54 times 10 to the minus 1, and then I've got to cube that. And when I plug that in, I get 6 times 10 to the minus 2. And so if I look back at my number line, I'm going to erase some stuff up here just to make it a little bit cleaner. My Q and my K are actually right on top of each other. So actually, I'm already at equilibrium, and so we would have no shift because Q is equal to K. Okay. What we want to be able to do is understand thermodynamic equilibrium in terms of relating delta G and K. And remember from your formula sheet, we have not used this formula just yet. That'll actually be in our last unit, so we can ignore that. But we want to remember that these two are delta G formulas. And delta G we can think of almost as a middleman. And what I mean by that is that if we are given K, we could get delta G, and from delta G we could then get voltage. On the flip side, if we are given voltage, we could get delta G, and from delta G we could turn it into K. Okay, so that is what we're going to do in this example problem. We are asked to get the equilibrium constant K, and we are given just the voltage. Okay, so what we want to think about is, okay, if we're just given the voltage, I want to think of how can I relate voltage to K, and there's not a direct way to do that, but I can take voltage here, get delta G, from delta G I can then get K, so that's what we're going to do. So the first thing I'm going to say delta G, and this little knot, that means standard conditions, which will be 25 degrees Celsius or 298 Kelvin. So delta G equals minus NF times E. Delta G, if you remember, is always going to be solved in joules per mole. It's always, always, always joules per mole. Okay. N is the number of moles of electrons that get transferred. So right now it looks like I go from +2 to +3, so that would be 1 electron. However, my coefficient for my chromates are 2, so this is really 2 total electrons. Okay, so this will be minus 2. Faraday's constant is given in our formula sheet. That's 96,485 coulombs per mole. And then the voltage is given. And here's what I know is it's a positive voltage, so that means spontaneous. And for a spontaneous process, that means it has to lose energy. So when I plug this into my calculator, I get a negative 1.29 times 10 to the 5th joules per mole. And that makes some sense to me, the fact that it's negative, because that means we are losing energy. Okay, so now I'm going to take this, I'm going to move it over here, and I'm going to say, okay, now that I have delta G, I can take my delta G, and that is equal to minus RT ln of K. Delta G is minus 1.29 times 10 to the 5th joules per mole. A common mistake students make in AP Chemistry is that they mix up R. R, there's two types of R. So let's write this out. R could be 0.0821 ATMs times liters divided by moles times Kelvin, or R could be 8.314 joules per mole Kelvin. Now, this first R, 0.0821, this is only for gas laws. This second R is everything else. So I've got to ask myself the question, is this problem that I'm working on right now, is this a gas laws problem? And hopefully you can say that it's not. So this R needs to be 8.314 joules per mole Kelvin. The temperature, we're at standard conditions, so that'll be 298 Kelvin. And then I don't know what K is, so I don't know what ln of K. I'm going to divide each side by negative 8.314 times 298. And what I end up getting when I divide is I get 52.18. That equals ln of K. I want to isolate K from this natural log. And so what I'll do is I'll take E to whatever number is on the other side. Here it is 52.18, so E to the 52.18 power. And so that'll make K be 4.61 times 10 to the 22nd. This K value makes sense. Here's why. We have a positive voltage. That means spontaneous. For a spontaneous process, it will lose energy. We did get a negative delta G. For a spontaneous process, it'll be a K value greater than 1 because products are in your numerator. And that's what we get here. Okay, so Hess's law. How do we add reactions? So what we want to be able to do is look at a reaction and figure out, has it been reversed? Is it still in the same direction? And if it's been reversed or if it's in the same direction, have the coefficients changed? Okay, so if I'm asked, I'm given K here, that K I'm going to use a lot. If I'm asked for the reverse reaction, that'll just be the reciprocal of K. So that'll just be 1 divided by 4.94 times 10 to the 71st. Okay, whatever that number is. Now, in example B, I've got to ask myself, okay, here are my two reactions. They look like they're going in the same order, so I know I am not taking the reciprocal of K. But these coefficients are all doubled. So whenever I double a coefficient, I need to change K, but I have to remember that coefficients go in the exponents. So if I double coefficients, I really need to square K, or double the exponent of K. So this will be 4.94 times 10 to the 71st squared. And that's a large number. That is actually 2.44 times 10 to the 143rd. That is a huge, huge number. Okay. Now, I got to look at this next reaction. It's going in the same order, so I know that it's just K. However, my coefficients are halved. So what that means is I'm going to half the exponent of k, or take the square root of k. So I'll take 4.94 times 10 to the 71st. I'll take it to the 1/2 power. Let me plug that in, 4.94 times 10 to the 71st to the 1/2 power. And I get 7.03 times 10 to the 35th. And then what I have in example D is I still have the same reaction. However, it is now reversed. So I know that it is 1 divided by k. That is the reverse. Then I want to look at the coefficients. The coefficients have been halved. So I know that I'm going to have half the exponent of k. So I get 1 divided by k to the 1/2. Or this is the same thing as k to the minus 1/2. Those are mathematically the same, so you'd have to plug that into your calculator and you would figure out what that is. This second example is really a Hess's Law question, and what it is I've got this overall reaction. Nitrogen plus oxygen plus bromine in a synthesis reaction gives me NOBr. So what I have is I have reaction A, or reaction 1, and I've got reaction B, or reaction 2. And I've got to figure out a way to get these two reactions to add up to be my overall reaction. Okay, so here's what I do, is I say, okay, my overall reaction has nitrogen. Where does nitrogen occur in this reaction? The only place just N2 occurs is in reaction B, and it's on the wrong side of the reaction. So what I know is I've got to flip reaction B. A second question I'm going to ask is the coefficient the same? And that is yes, so I'm pretty sure that I won't have to multiply reaction B by anything. Okay, I've got nitrogen taken care of. Oxygen. The only place oxygen occurs as O2 is in this second reaction, and it's on the wrong side, but I have already flipped the reaction, so that looks good. Bromine. The only place bromine occurs is in reaction A. It's already on the correct side of the reaction, so that's good. And the coefficient is already the same, so I'm pretty confident that reaction A will stay the same. And then 2NOBr. That is on the product side of my overall reaction, and it is on the product side of reaction A, so that looks good, and its coefficient looks good. So what I need to do is I need to combine reaction A and B, and when you combine reactions, you multiply the K's if you want to know the K for the overall reaction. So what I'm going to do is I'm going to take Ka, which that is 2.0, K from reaction A. I'm going to multiply it by Kb. However, since I flipped the reaction, it really needs to be 1 divided by Kb. So I will take 2 times 1 divided by 2.1 times 10 to the 15th. And I'll plug that into my calculator. And what I get is I get 9.52 times 10 to the minus 16 as my K for my overall. So that equals K for the overall reaction. Okay? Okay, let's look at different types of rice table problems. These will be good reactions to make sure you understand. The first one that we have is we've got a reaction, and always make sure your reaction is balanced. This one is balanced. And we're given some clues that this reaction initially has 0.298 moles of PCl3, 8.7 times 10 to the minus third moles of PCl5, and it doesn't mention anything about chlorine initially, but at equilibrium, and that is a key word, we've got 2 times 10 to the minus third moles of chlorine. And I want to calculate the value of each species at equilibrium and K. So what I'm going to do is I'm going to set up a rice table where R stands for reaction, I stands for initial concentration, C stands for change, and E stands for equilibrium. Remember, what you plug into a rice table, you can only plug in molarity or pressure. Okay, so you cannot plug in moles to a rice table. What I'm going to say is that the initial concentration here, since it's 1 liter, that makes the math a little bit easier, that PCl5 over here is 8 times 10 to the, 8.7 times 10 to the minus third. PCl3 is 0.298 molar. And then chlorine is 0. Once I have my initial, I want to think which way does the reaction shift. If I have numbers for everything, then I have to solve for Q. However, here, my chlorine is 0, so what that means is that at equilibrium, I have to have some of everything. That's what equilibrium is. And so what I know is that the reaction has to shift right to form some chlorine. So this will be minus 1x, minus 1, or plus 1x, and plus 1x. So this will be 8.7 times 10 to the minus third minus x, 0.298 plus x, and then x. I'm going to write my K expression, and remember, with a K expression, you always want to write it without any numbers because you will always get 1 point for just writing the K expression, okay, even on the AP test. So it's kind of what I consider to be free points. Okay. So what can I plug in? I know that PCl3 is going to be 0.298 plus x. I know Cl2 is just going to be x, and then I'm going to divide that by PCl5, which is going to be 8.7 times 10 to the minus 3 minus x. And all I've done is I've just plugged in my equilibrium concentrations from my equilibrium row. And this equals K. And now I've run into a little bit of a problem because I need to solve for K, and I need to solve for the equilibrium values of everything. So what that means is that I have 2 unknowns, and I must have a clue as to what one of them is. And that clue is this 2 times 10 to the minus third moles of Cl2. And that is at equilibrium, so x actually equals 2 times 10 to the minus third moles, or molar, for Cl2. And now I'm going to plug that in. And I'm going to move some things around to make life a little bit easier. When I plug in x, I get 6.7 times 10 to the minus third molar for PCl5. So I can change that down here. I get 0.30 molar for PCl3. So I can change that down here. And then for chlorine, that is just x. And so that'll be 2 times 10 to the minus third. And if I math this out, that'll all be K. And that equals 8.96 times 10 to the minus second. So that is K. So I've answered the question. Last thing I like to do is just say K is less than 1. So this is reactant favored. Okay, so that is one type of rice table problem. A second type of rice table problem looks something like number 2, where we've got a reaction between hydrogen and fluorine, and they form HF. Make sure it's balanced. And they give me the equilibrium constant is 115, so I'll say K equals 115, and that is product favored. And I'm going to set up my rice table. We have 1.5 liters, and we have 3 moles of each chemical initially in 1.5 liters. 3 moles divided by 1.5 liters will be 2 molar. So I'll start out with 2 molar of everything. And I'll have to figure out which way the reaction shifts. Well, I have values for everything, so I don't know which way it shifts. Some people would say that it's product favored, so it should shift to the right. And I would say, okay, you're kind of on the right track, and you're probably not wrong. But what if we swapped these 2 molars with like 10 billion molar? Then, even though it's product favored, 10 billion molar would be a large concentration, so then maybe we don't know exactly. But we can prove it by solving for Q. So Q is equal to HF squared, don't forget to square it, divided by H2 divided by F2. So I can plug this in. Q is equal to 2 squared divided by 2 times 2, so Q equals 1. Can compare that with my number line. K equals 115. Q is all the way over here at 1, so we must shift right, okay, because we will always end up back at equilibrium. It's kind of what we predicted, but we proved it here. So H2 will be minus 1x, F2 will be minus 1x, and HF will be plus 2x. Don't forget that the coefficient of 2 will impact how many x's are added there. I'll add up each column, 2 minus x, 2 minus x, and then 2 plus 2x. Write my k expression. K is equal to HF squared divided by H2 times F2. And that equals 2 plus 2x squared divided by 2 minus x, 2 minus x. To simplify this, I'm going to combine those and make that 2 minus x squared, and that equals 115. What we're solving for is the equilibrium concentrations of everything. So essentially, if I can get x and I just plug it back into this E row, I will be good to go. So some people will try to use the 5% rule here. The 5% rule is a rule that says you can get rid of all minus x's and plus x's so long as there's still an x around. But if I get rid of plus x and minus x there will be no more variables around, so I must not be able to do that. What I can recognize is that both the numerator and denominator are squared, so I can actually take the square root of each side, and I can then see that I will get, I'm going to make this a little bit smaller. Okay, I will end up getting 2 plus 2x divided by 2 minus x equals the square root of 115, which is 10.72. I will now multiply each side by 2 minus x. Okay. So now what this simplifies to is I have 21.44 minus 10.72x equals 2 plus 2x. I will combine like terms. I'll add over 10.72x and then I'll also subtract away 2, and I'll end up with 19.44 equals 12.72x. If I take all that, what I'll eventually get is that x equals 1.53. Okay, and then I'll just plug that back in. And the final answer that you will get is that H2 and F2 are actually the same, and they will be 0.47 molar, and then HF will be 5.09 molar. Okay. Number 3 here is probably the most common type of rice table problem that we see. What we have is we've got methane reacting with iodine. They give us the K for this reaction. K is 2.26 times 10 to the minus 4. And they give us a temperature. The only reason they give us a temperature is that's the only time in which that K value is true. And what I'm going to do is I'm going to set up a rice table, and I'm going to copy this. Oh. Reaction and okay. And it's already balanced. I'm going to set up a rice table. And this one looks like we're using Kp, so everything will be pressure. The initial pressure of methane, which is CH4, is 105.1 torr. And iodine is 7.96 torr. And we are asked to figure out the pressures of everything at equilibrium. And then is Kp and Kc equal? I'll answer that second question first. Kp and Kc are equal for this reaction just because we have the same number of gas moles on each side of the reaction. Okay, that's the only time when Kp and Kc are equal. So this initial concentration of those guys are 0. Because of that, we must shift right. So that'll be minus 1x, plus 1x, plus 1x. So 105.1 minus x, 7.96 minus x, and x. Write your K expression just to get a point. CH3I times HI. And we're going to divide that by CH4. I2. We can plug in what we know. I know that CH3I is x, HI is x, and then I also know that CH4 is 105.1 minus x, and I2 is 7.96 minus x. So what this simplifies to is this will be x squared in the numerator, and this all equals 2.26 times 10 to the minus 4. So this is a quadratic formula equation, but I don't really want to solve it out that way, so I'm going to use the 5% rule. And here is why I can use the 5% rule. It's very important that you know when you can and when you cannot use the 5% rule. The 5% rule is used when you can have a quadratic formula type equation, and you can get rid of a minus x or plus x, I mean, same difference, any adding or subtracting x's, and you're still left with an x. So for example, I got rid of this minus x and minus x, but I'm still left with an x in the numerator, so that is okay. So what this simplifies to is I just get rid of that, and I'll multiply my denominator, and I will get 836.596, and multiply each side by 836.596, and I get x squared equals 0.1891, and then x equals 0.435. To finish solving the equation, just plug back in x. Okay, and that will get you the equilibrium concentrations or the pressures of everything. Now, this should make sense. My K value is pretty low. It's way less than 1. So even though I started out with 105.1 torr, not very much of that is going to react. And in fact, of the 105.1 torr, only 0.435 torr actually reacted. And that's something that we should be able to anticipate just because it is reactant favored. Okay, so let's talk about KSP. And KSP is something that is a little bit tricky until you get the hang of it. And KSP, okay, if you are given a KSP value, make sure your reaction matches that. So for example, let's say I was given the KSP of AgCl. That means my reaction needs to look like a KSP reaction. And a KSP reaction is where you take a solid and it breaks apart into its ions. So what will this look like? It would be AgCl breaking apart into Ag plus 1 and Cl minus 1. Both of those aqueous. And this is a solid. It could be different. What if we had iron chloride? So that might be like iron 2 chloride. This would be Fe plus 2, and then we would have 2 Cl minus 1. This is chloride, not chlorine. Okay, so it doesn't need to be diatomic. I know that that's a subtle difference, but we got to make sure we can do that. So, also with KSP, your molar solubility is only for solids. Okay, so that'll be just for this guy if we're talking about molar solubility. And we're going to use the variable x for molar solubility. So let's see what this looks like. Is in number 1, I have copper 1 bromide. And with copper 1 bromide, it has a molar solubility of 2 times 10 to the minus 4. So the first thing I'm going to do is I'm asked to solve for KSP. So I'm going to write my reaction. CuBr, solid, will break apart into Cu plus 1, aqueous, plus Br minus 1, aqueous. I'm going to set up a Rice table. And what I know is that this is copper bromide. It's a solid. It's not included in an equilibrium expression. Okay, so when I end up doing my KSP will be equal to Cu plus 1 times Br minus 1. And I don't have an initial concentration for copper or bromine, but I know that we'll shift right because we have to have some of everything. So what we end up with is x and x for those two, or x squared. And molar solubility is our variable x, so this will just be 2 times 10 to the minus 4. We'll square it, and so that'll be 4 times 10 to the minus 8 as our KSP. Okay, let's look at something like number 2. It's going to be the same exact thing, except Bi2S3 is a little bit trickier just because of how it breaks apart. We're going to have 2 bismuth plus 3 ions, plus 3 sulfide ions. This is a solid, so that'll be x, 0, 0, plus 2x here, plus 3x here. And so KSP is equal to the concentration of Bi plus 3 squared times S2 minus cubed. I'm going to plug in what I know. Bismuth is 2x. Sulfide is going to be 3x. And I can simplify this. This right here, 2x squared. This is where people tend to go wrong. That'll be 4x squared. And then 3x cubed. That will end up being 3 cubed is 27. That'll be 27x cubed. Then I can simplify this again. This will end up being 108. And then x squared times x to the third is x to the fifth. So this will be 108 x to the fifth, which equals 108. The x value is the molar solubility, 1 times 10 to the minus 15. And then we'll times that to the 5th power. And so we will end up getting 1.08 times 10 to the minus 73rd as our K value. What you could do is you could also plug in to x earlier in your Rice table, and you'll still get the same answer. Now, what if we're asked to solve for the molar solubility and we're given KSP? So first, write your reaction. CuIO3, 2 breaks apart into Cu plus 2 iodates. Make a Rice table. This is solid, and then your ions are always going to be aqueous. And we're asked to solve for the molar solubility. So this will be 0, 0 plus x, x plus 2x, x. So our KSP equals Cu plus 2 IO3 minus 1 squared. And so what I can do is plug in copper. Copper is X. Iodate is going to be 2X. 2X squared is 4X squared times X. This will be 4X cubed equals the KSP that was given, which is 1.4 times 10 to the minus 7. When I solve for X on this one, I end up getting 3.27 times 10 to the minus third. Okay, most students do okay with these. One thing that people goof up on all the time is with common ions. I would know solubility always decreases when you have a common ion. Okay, here's why. That if I have a KSP value for PbF2, that means PbF2 is what I'm going to start my reaction with, and it's going to break apart into Pb plus 2 plus 2F minus 1. And what this will be is I'm going to make a saturated solution. All of what I have will dissolve. PbF2 we would say is insoluble according to solubility rules, but some of it will dissolve just a little bit. And so if there's a common ion, we have some lead. What that means is that I'm already on my way to getting saturated. If I just try to dissolve in water, it's like I start at a point of 0. So nothing's been in there to help me get that solution saturated. But if I have a common ion, that means I'm on my way to getting saturated, so it's not going to be able to dissolve as much because it's already on its way there. So this solid will be X, lead will be 0.1 instead of 0, and then fluoride will be 0. We will still shift right, so plus X and plus 2X. We get 0.1 plus X, and then we get 2X. The KSP equals Pb plus 2, F minus 1 squared. Pb is 0.1 plus X, and then F is 2X, and we'll square that. And that will equal the KSP, which is given 4 times 10 to the minus 8. This is a quadratic, and it's ugly. I don't really want to deal with a quadratic, so what I'll do is I'll use the 5% rule, which says I can get rid of any x's that are being added or subtracted so long as there's still an x remaining. So I get rid of that guy, and this 2x is still remaining. So I'm going to do that. And so I'm going to have 4 squared times 0.1, so I'm going to have 0.4 x squared equals 4 times 10 to the minus 8. When I simplify, I am going to get 4 times 10 to the minus 8 divided by 0.4. Take the square root of that. I end up getting 3.16 times 10 to the minus 4 for my molar solubility, because that's what x is. And then I'd even put the unit m on it. Okay, last problem here. I'd know how to do something like this. How do you know if a precipitate will form if you mix two solutions? So, here's key word. You're mixing two solutions, aka that is a dilution because volume is changing. So, the dilution formula is M1V1 equals M2V2. What I need to do is I need to get my reaction. But here's where a lot of students goof. I'm given barium chloride and potassium sulfate. Those are what's being mixed. So a lot of students will do a double replacement reaction there. And I think, okay, you're fine. That is correct. That will be what's happening. But as far as what my math is concerned in terms of a precipitate, I'm looking at K. And so I want to make sure that my reaction matches my K. I'm given a K for barium sulfate, and it's a KSP. So I need to start with barium sulfate solid, breaking apart into barium ions plus sulfate ions. And what I need to do is I want to just figure out what is barium's concentration and what is sulfate's concentration. Once I know that, I can plug that into a QSP problem, which will be Ba plus 2 times SO4 2 minus. And once I get Q, I'm going to compare it to K. K is 1.08 times 10 to the minus 10. And if I can just compare that to my Q value, let's say Q is over here, then I would shift right. These guys are aqueous, so that would not be a precipitate that's being formed. Let's say my Q is over here, then I would shift left and I'd be going towards the solid, and that would mean a precipitate is being formed. So I've just got to get Q. The way I get Q, again, is I just have to figure out the concentration of barium and of sulfate. Once I know that, I will be good to go. So barium concentration, what I'll do is M1V1 equals M2V2. The initial concentration of barium was 4 times 10 to the minus third. The initial volume was 200 milliliters. The new molarity of barium is what I'm trying to figure out. And the volume, if I take 200 and I add 600, that'll be 800 milliliters. So let me just plug that in. 4 times 10 to the minus third times 200 divided by 800. I get the molarity of barium is 1 times 10 to the minus third. Okay, looks good. I'm going to erase that, and now I'm going to do sulfate. Same formula, M1V1 equals M2V2. The initial molarity of sulfate was 8 times 10 to the minus third. The initial volume was 600 milliliters. The new molarity is what I'm trying to solve for, and the total volume is going to be 800 milliliters. So when I plug that in, I'm going to get the new molarity of sulfate is 6 times 10 to the minus third molar. So then what I'm going to do is I'm just going to plug that into Q and see what I get. So I can get rid of barium. I'll move this into where barium was. Oops. And then I'll take sulfate. Get rid of sulfate here. And I will just move the sulfate concentration in there. And when I math those out, my Q that I end up getting is 6 times 10 to the minus 6. So that is much larger than times 10 to the minus 10. So Q is over here at 6 times 10 to the minus 6. So we will shift left. The reasoning why is Q is greater than K, and a precipitate will form. Okay.